Hello everyone, I'm Yuanzhu Zhang from Pennsylvania State University. I'm glad to share our results on error manipulation with contact-aware onboard perception and hybrid control. While UAV has been traditionally confined to passive roles such as inspection and surveillance, recent advances in error manipulation have enabled active, contact-based interaction with environment. As shown in these demonstrations, UAVs can perform pick-and-place in the wild, doing light bulb mounting on the wall, execute valve turning with accuracy. Beyond industrial tasks, they are also capable of lateral drawing, coordinating flight motion with controlled contact forces. Although this demonstration highlights the potential of error manipulation, the tasks are either performed without regulating the interaction forces or rely heavily on external motion capture system for accurate state estimation. In real-world deployments, however, such external tracking is unavailable, and the GPS may be unreliable near the infrastructure. These limitations underscore the need for fully onboard perception and control to enable precise error manipulation in practical scenarios. We consider a packing hole task with force regulation as a representative error manipulation scenario. In this task, the UAV needs to visually approach the target, align the end effector with the hole, establish a physical contact, and then maintain a desired normal contact force. Our robot platform is a fully actuated exter UAV. Unlike conventional multi-rotor, this platform can regulate its position and attitude more independently, which is especially useful for our precise error manipulation task. The robot is equipped with a 0 degree of freedom manipulator arm mounted at the front, together with a force torque sensor for measuring the interaction force. And also, all perception and control are performed on board using the onboard computer, cameras, and IMU. To address the challenges of precise error manipulation under contact, we propose a unified, contact-aware onboard perception control pipeline. A contact-aware visual inertial odometry module fuses camera, IMU, and force torque measurement to provide robust state estimation and activate the contact factor during interaction. An image-based visual servo, or we call it IBVS, guides the vehicle during the approach phase. The contact-aware VIO module will consistently provide velocity estimation for the IBVS module. While upon contact, a hybrid motion range controller regulates forces along the wall normal direction and tracks the lateral motion. Finally, the control allocation module maps the commanded ranges into rotor speeds for execution on the fully actuated hex rotor platform. We formulate our contact-aware VIO as a standard vector graph optimization problem, but augment the optimization goal by adding contact constraints. The first three terms in the orange box are classical residuals in general VIO. The last term shown in the blue box is a residual from contact. Specifically speaking, when the UAV makes contact to the wall, we impose position constraints to restrict the motion along the wall normal and velocity constraints to suppress undesired sliding. We design a hybrid motion and force controller for our error manipulation task. The main idea is to decompose the control input into two parts, a motion controller driven primarily by visual servoing, and a range controller mainly for contact force regulation. By following the standard IBVS formulation, we define the aerodynamics directly in the image space, and then we can easily get the desired camera twist. It will be further transformed to desired body twist. Finally, the low-level PID controller will compute the desired range underlying. On the other hand, the range controller is implemented as an impedance controller to enable compliant contact establishment. In the experiment, we firstly evaluate our framework using a pegging hole task in simulation. The UAV is guided to the target by the visual servo, while state estimation noise is gradually added to emulate real-world conditions. Upon contact, force control is activated to regulate the interaction force at 5 newtons. The results show stable guidance and effective regulation of the desired contact force under various velocity estimation noises, which proves the robustness of our proposed framework. We further evaluate the proposed pipeline in real-world experiments. The flight relies solely on onboard sensing without the aid of an external motion capture system. In contact, our contact-aware VIO activates contact constraints, which effectively anchors the vehicle to the environment. It improves the estimation and yields more stable velocity estimates along the contact direction, enabling reliable interaction during manipulation. Finally, to summarize our contributions, first, we propose a contact-aware onboard perception control pipeline for contact-rich area manipulation without external motion capture system. Second, we augment vector graph VIO with contact consistency constraints to improve estimation performance during contact. Third, we develop an image-based visual servoing scheme that couples with hybrid force motion control for compliant contact. Thank you very much for your attention.